we're going to look through the first part of Chapter 15's Probability Rules. So in the first part of Chapter 15, here are 3 goals. We want to be able to answer, how do I use the general addition and multiplication rules? What is conditional probability? And then how do I prove 2 events are independent? So probability is one of these things that can get so complicated so quickly. But then there's sometimes a tendency to overcomplicate things, okay? So I'm going to try to keep this as simple as possible. So sometimes there's going to be a rule that applies, and I'll show you both ways, but I'm hoping that you can latch on to whatever's simplest for you. Okay, so I'm showing you the sample space for a deck of cards, just because I found that, sometimes kids don't even know what's in a deck of cards, which is fine. Okay, so 52 cards in a deck, half the deck's red, half the deck's black. We've got 13 cards in each suit, which would be my clubs, spades, and then hearts and diamonds are red. Okay, so the first question, 1 card is drawn. What's the probability of getting an ace or a red? So probably the easiest way to do this is just look at your sample space and count the number of aces, and I see 4, and then how many red cards? Well, there would be half the deck, which is 26, but you got to be careful because you already counted 2 of the red ones because they were aces. So it would be 4 plus 24, or 28 out of 52. So that's as a fraction, which we can reduce to 7 out of 13, which as a decimal would be approximately 0.538. Now, we're going to be talking about the general addition rule here in a second. These are not what we call mutually exclusive events, so we can't just add them. But we can add them if we remember to subtract the overlap. So I could have done this by going, okay, probability of an ace is 4 out of 52, which, yeah, I know it reduces, but I need common denominators with fractions for addition and subtraction. Plus 26 out of 52, but then I have to remember to subtract my overlap, which was 2 out of 52. Okay, so we're going to put this in a more formal language with an actual rule here, but I think it's conceptually pretty easy to understand. Okay, 2 cards are drawn without replacement. Okay, so if we're not replacing a card, these are definitely not independent events. We have to refer to these as dependent events. So we want to know the probability that both cards are aces. Well, you would have 4 out of 52 would be your chance for the first. Now the key is you assume that you're successful. So now there are only 3 in the deck and 51 remaining. So if we multiply this together, this is going to be 3 out of 663. Or approximately 0.0045. You'll notice I'm probably a little inconsistent with how many decimal places I go to with probability. There's not a rule of thumb on the AP exam. You just want to go out to several digits of precision. Okay, now 5 cards are drawn without replacement. Find the probability that all of them are spades. All right, you pause and see if you can put into practice what I did in the last example. So what have I done? I've dropped both the numerator and denominator by 1 value for each card that's drawn. Throw this in the calculator. And I can small chance of drawing 5 cards that happen to be all spades. Okay, so on our continuum of certain to impossible, it's definitely closer to the impossible. All right, 1 card is drawn. Find the probability that you draw a heart given that it is red. So what does this mean? This means, what's the chance that you drew a red card? What's the probability that it's a heart? Well, of the red cards, half of them are hearts. I want you to notice this notation though. This vertical line right here is stating what's the probability of getting a heart given that it is a red card, right? We're going to look at this again. It's known as conditional probability, and there's an actual formula that is given on the AP formula sheet that we'll look at more closely. All right, next one says 1 card is drawn. Find the probability of drawing a red card given that it's a heart. Well, if you drew a heart, what's the chance that it's red? It has to be red. This would be equal to 1. All right, let me just zoom out for you. In 6, it says 1 card is drawn. Find the probability of drawing a red or a face card. So as I look at this, how many are red? That's 26. How many are face? That would be all the ones with faces. That's these over here. So red would be 26, and then I count up these 6 more would be 32 out of 52, which as a fraction is 8/13, and as a decimal is about 0.615. Finally, 7, 1 card is drawn. Find the probability of drawing a red and a face card. So which ones are red and face? I see 6 would be these 6 right here, and that's 6 out of 52 then, which reduces, and as a decimal is 0.1154. I will revisit 1 or 2 of these in a more formalized way in a second, but we're going to go into our actual formulas. And I want to point out that you have 2 probability formulas on your AP formula sheet. So I encourage you to get that packet out so you're in the habit of referencing it as you go through these problems. This first one on the left is our general addition rule, saying the probability of getting event A or B, union is or, means we add them together, but if they're not mutually exclusive, we definitely need to subtract. You know, you can always use this rule because if they are mutually exclusive, you'd be subtracting 0. So you already know the formula for mutually exclusive events. It's the addition rule. If they're disjoint, there's my little Venn diagram, all we do is we add our 2 probabilities together. But as I was just stating on the previous slide, when I have my general addition rule, here's the formula from your formula sheet. What do? We add the 2 together, but we need to subtract the intersection, which is the probability of A and B. Because if you don't subtract this intersection here in the middle, you're counting it twice, okay? As I previously stated, the general addition rule will always work, so it's not like you need to memorize 2 separate things. Okay, so two-way tables and Venn diagrams are often, I'm a visual learner, I often need to draw pictures when it comes to probability. I love Venn diagrams, they're kind of my go-to thing. So if I have 2 sets, which I'm not going to get super creative here, I'm just going to say set A and set B, okay, and I'm just going to describe the different areas. So my overlap is the intersection. This would be A but not in B, this is in B but not in A, and then not in A or B would be this area out here, which I'll call area 4. How does that correspond to a two-way table? Well, so I have event A and event B. So if A and B happens, that is this area right here. So that corresponds, these 2 numbers will be the same. If A does not happen, and I'm going to put B complement or B does not happen right there, what does that correspond to? Well, this area 2, so this is in A but not B. So in A but not B is right here. So I'm going to put a 2. In B but not in A is 3. And then B complement, A complement, or not in either set is area 4. So that's how a two-way table and a Venn diagram kind of correspond, right? Just in general, what numbers will match up. So I just want to jump back to this example and illustrate that number 1, I actually used the general addition rule where I added the 2 together and I subtracted the overlap. I could have done the same in my number 6, I think it might be labeled as letter F in your notes, which would be the probability of a red or a face. How do I do that? Well, that's the probability of a red plus the probability of a face minus the overlap, which is the probability of red intersected with the face card. So mathematically, what would you do? Probability of a red is 26 out of 52, plus the probability of a face card. There are 12 face cards, and then you subtract the intersection. The probability of red and face would be minus 6 out of 52. But like I said, I think this is so much easier how we did it before. Just look at your sample space if you have it. We're going to look at an example from the textbook. It says a survey of college students found that 56% live in a campus residence hall, 62% participate in a campus meal program, and 42% do both. Okay, so these are definitely not mutually exclusive or disjoint events if 42% do both. So what's the probability that a randomly selected student either lives or eats on campus? So I like to abbreviate. I'm going to say lives on campus is equal to 0.56. So I'm letting, and I wrote 0.56, where a capital L will be lives on campus. And then I'm going to say probability of M, meaning they participate in the meal program, is 0.62. So what's the probability that they live, capital L, or, so or would be union, eat on campus, so meaning in the meal program. Probability of L in union M. So what's this equal to? Well, 0.56 plus 0.62, but I definitely need to subtract my overlap, which I'm told is 0.42. So do the math, it's a 0.76, okay, or 76% chance. All right, we're going to draw a Venn diagram out of this. Honestly, I probably even would have done that before part A, but I'm just following along here with what's on my paper. So I'm going to make my two circles overlap. This will be L, and here is M for in the meal plan. So I know that 0.42 do both. Just gonna zoom in here to give myself a little more space. 0.42. 0.56 total live on campus. So I've got to do 0.56 minus 0.42, which would be 0.14 in this area. Meal plan was, got to zoom back out here, was 0.62. So that's going to mean that there are 0.2 here in this area. And then what about do neither? Well, this has got to total to 1. So that means I would have 0.24 remaining. Now whatever probability questions are asked become pretty easy. So probability lives off campus and no meal plan. So probability of lives off campus would be L complement intersected with meal complement. So what's that? That's this area down here, the outside, both circles. Probability lives on campus and no meal plan. So just showing you proper notation would be lives on campus, intersected, no meal plan would be complement. What area is that? That's over here, this area, right? So 0.14. So you could try to get fancy with formulas, but I tell you it gets pretty confusing pretty quickly. Go with a Venn diagram, so much easier. Okay, another book example. Police report that 78% of drivers stopped on suspicion of drunk driving are given a breath test, 36% a blood test, and 22% both tests. So I am, even before I go into answering any questions, I'm going to draw my diagram. So I'll put breath versus blood test over here. 22% do both. I always start in my middle, 0.22. What else am I given? 78% are given a breath test, so this whole circle needs to have a total of 0.78. So if I have 0.22 here, 0.78 minus 0.22 is 0.56 in this region. And 36% a blood test, so this whole circle needs to add to 0.36. So if this is 0.22, that remains 0.14 here. Altogether, this needs to add to 1. So if I see what's remaining, this all adds to 0.92. So that means 0.08 would be neither breath nor blood test. Okay, so number 1, what's the probability that a randomly selected DWI suspect is given a test? Well, I think we just answered that. Probability of a test was 0.92. It was all 3 of these values added together. Okay, wouldn't hurt to put that into a sentence. 92% of all suspects are given a test. Next, what is the probability of a blood test or breath test, but not both? Okay, well, that would be this area, 0.56, plus this area here. So that would be a 70% chance, and probability of neither test would be 0.08. Just curious, how do you show that in notation? Probability of neither test, you could write that as 1 minus, because it's the complement, the probability of our union. So breath, union, blood test. All right. In the next example, you're given a two-way table. So you could convert this to a Venn diagram if it's your preferred way, but I want to show you actually how to work with two-way tables. First of all, what is the relationship between educational achievement and home ownership? A random sample of 500 U.S. adults was selected. Each member of the sample was identified as a high school graduate or not, and as a homeowner or not. The two-way table displays the data. Suppose we chose a member of the sample at random. Define events. So G is a person who is a high school graduate, and H is a person who is a homeowner. Okay, so I always begin by finding my marginal frequencies, which means I'm just adding 221 plus 119 is 340. 89 and 71 is 160. I'm going to find my marginal frequencies down here. 221 plus 89 is 310. 119 plus 71 is 190. And then I add, and what do I get both directions? I better get the same value. I get 500. That's a good thing. Okay, now explain in plain language what probability of G complement means, and then find that probability. Hopefully you stated, well, that's just the probability that the person did not graduate high school. Now that we have our marginal frequencies, I'm just going to look here. That's my 190 out of my total 500. So 190 out of 500. Let's change this into a decimal form for its proportion would be 0.38. We could also say 38%. Next, explain why the probability of G or H is not equal to the probability of G plus the probability of H. So what are they saying is, why can't I just add them together? Well, because there's probably an overlap. Well, what does that mean in the context? Well, being a high school graduate and a homeowner are not mutually exclusive. There are definitely people who are both high school graduates and homeowners. So how do we do this? Well, we're going to use our general addition rule. So mathematically, we can see the probability that you're a high school graduate was 310 out of the 500 sampled. Probability that you're a homeowner, that total marginal frequency is 340 out of 500, but we've got to subtract the overlap, also known as our joint frequencies. So probability of G intersected with H is this value right here, where the two intersect. So 221 out of 500 needs to be subtracted. So let's see what that equals. Toss those numerators in my calculator would be 429 out of 500, which is 0.858. Now take a second and see if you can take these values in the two-way table and make them into a Venn diagram. So here's my Venn diagram. Notice that I am using just frequencies. These are not relative frequencies or proportions, okay? These are just the raw counts, so just frequencies. Okay, so finally we're asked, write the event is not a high school graduate, but is a homeowner in symbolic form and find the probability. So probability that it is not a high school graduate, so that's G complement, because it's not, G not, intersected with homeowner. Okay, so what is that? Again, let's just look back at our two-way table. So G not, so not a high school graduate, is over here, but is a homeowner. Okay, yeah, that's 119 out of 500. Which is approximately 0.238. Okay, so 2 psychologists surveyed 478 children in grades 4, 5, and 6 in elementary schools in Michigan. They stratified their sample, drawing roughly 1/3 from rural, 1/3 from suburban, and 1/3 from urban schools. Among other questions, they asked the students whether their primary goal was to get good grades, to be popular, or to be good at sports. One question of interest was whether boys and girls at this age had similar goals. Here's a contingency table giving counts of the students by their goals and sex. So notice it's called a contingency table. Also, why contingency table, not two-way? Well, I've got more than 2 variables here, okay? So generally just called a contingency table. So what is the probability that a selected student wants to excel at sports given that we have selected a girl? Okay, so let's talk, this is actually conditional probability that you read about in your text. So the probability that they want to excel at sports, so sports, given, it's a vertical line, given that we've selected a girl. You read about a formal way of doing a calculation, but I think a two-way table, or I'm sorry, contingency table makes this pretty easy. So here's sports, so 60-30, total of 90, but which of these frequencies am I going to use? I'm going to use this, 30, because sports, given that it's a girl. So that would be 30, but what's it out of? Well, given that it was a girl, the total number of girls would have been 30 out of 251, which, change that as a decimal for my proportion, is approximately 0.1195. Okay, so what about the probability of sports given that it's a boy? All right, so sports would be 60 out of 227, which is approximately 0.2643. So what conclusion can we draw here? What were we interested in? One question of interest was whether boys and girls at this age had similar goals. So now I've guided you through this because I'm telling you to look at sports given a girl, sports given it's a boy. You could have looked at their grades. You could have looked at, not sure what popular means. Oh, what their primary goal was, was to get good grades, to be popular. You could have analyzed any of these different categories. I just chose to analyze sports. Well, what can we conclude here? I am stating that the interests are not the same. In these 478 students in Michigan, boys are more than twice as likely to prefer sports than girls. Okay, so I want to talk about conditional probability in a more formal way. We looked at it with contingency tables, but what is the probability of getting A given that B has already occurred? Now I'm going to tell you, if I'm given a contingency table, I'm not touching this formula, okay? I'm going to do it how I showed you in the previous one. But the formal formula that is on your AP formula sheet, I just took a screenshot of it, is right here. Probability of A, given that B has occurred, is equal to the probability of the intersection of A and B divided by the probability of just B. So we're going to revisit our meal plan and living on campus example to show how, or a time where you could use this formula. So we had found that 56% of college students live on campus and 62% have a meal program and 42% do both. So you're stated, while dining in a campus facility open only to students with meal plans, you meet someone interesting. What is the probability that your new acquaintance lives on campus? So I'm going to put it into formal writing here. What's the probability that they live on campus, but what was given? Okay, it's not just what's the chance somebody lives on campus, but given that they had a meal plan because you're in a dining hall open only to people with meal plans. So what is this equal to? Probability that you live on campus intersected using my formula with the meal plan divided by probability of the second one, okay? This one here, probability of meal plan. You don't have to memorize this formula, but you do need to get in the habit of having that formula sheet next to you. Okay, so what is that? Probability of the intersection is 0.42 divided by probability of a meal plan. What are all my ones with meal plans? Was 0.62. Do the math, that's 0.677. Which this now leads me to my last rule, my multiplication rule. Well, we've already talked about, if you have independent events where one event does not impact another, which if everything were only ever about dice, we would probably be good with just saying, oh, well, we just multiply our two probabilities together. But probability gets more complicated than that because there's a lot of real life scenarios where things are not truly independent, that one event some way does impact the others. So my general multiplication rule, which is the probability of A intersected with B, I'd love to just be able to multiply my two things together all the time, but I have to think about, it's still the probability of A times the probability of B, but given that A has already occurred. All right, so there's my difference, not just multiplying it. So think about that. If it's not independent, think of the one we did at the very beginning where if I draw a card from a deck and I don't put it back, it's the probability of A times the probability of B given that A has already occurred. Now, I just want to talk about how do we prove two events are independent. This is always huge on the AP exam. Okay, so I'm going to kind of talk you through this logically. So if the probability, two things are independent if this is true. Okay, so the probability of A is equal to the probability of A given that B happened. Okay, think about that. So two things are independent if B happens, but it didn't impact or change the probability. So if you compute these two and we have a conditional formula to calculate this on your formula sheet, if the two decimals are equal, then you can conclude that they are independent. Okay, it could be written the other way, saying the probability of event B is equal to the probability that B happened given that A already occurred. Okay, so I got a lot of notation going on. You're gonna have to give me some study time. I know this video has been really lengthy. Let's do one last example. Zoom in here so you can read it again from your textbook. Our survey told us that 56% of college students live on campus, 62% have a campus meal program, and 42% do both. Are living on campus and having a meal plan independent? Are they disjoint? Okay, so I'm going to put some notation here again. So this, I'm going to say probability of L, I believe is what I called it before, living on campus. Meal program, I'm going to say probability of M. And then both is probability of L intersected with M right here, the 0.42. Okay, so I'm actually going to answer this one first. Are they disjoint? No way. Okay, we got a 42% do both. So you can pause and read my answer in context there. Now, how about the independence? So let's analyze that. To do my independence check, what do I need to do? Well, the probability of having a meal plan has to be the same as probability of a meal plan given that you live on campus. Now, I could do this slightly differently. I could say probability of living on campus has to be the same as the probability of living on campus given you have a meal plan, but I think that's a little bit counterintuitive. So I'm going this direction. You'll never have to go one direction. All right. So probability of a meal plan. Well, I know that value. That's 0.62. So I'm going to plug that in underneath here. And I'm checking, is this equal to probability of a meal plan given that they live on campus? Well, how do I get that? That's conditional probability, which I have a formula for that. So just reminding you what it is, there it is from my formula sheet. That's equal to the intersection of my events, which I know is 0.42, over probability of just living on campus, which is 0.56. Are they equal? Let's see, that's 0.75. So I'm just going to bring this down, 0.62. Does that equal 0.75? No way. So my conclusion here is the events are not independent. Students who live on campus, so that's this probability here, students who live on campus are more likely to have meal plans. I know that was a ton of content I just threw your way. You need to do some practice and more practice and more practice now.